Gauss-Jordan Elimination. This method of solving for a system of linear equations involves matrices, row reduction, row operations, and getting the matrix into reduced row echelon form. We'll touch on these terms in a minute, but for now let's credit who came up with this awesome method. Carl Gauss and Wilhelm Jordan came up with this in 1888. While their names aren't that important, their mathematical ways are. So let's get into the fun math part. To begin, you must know what row reductions are allowed. There are three different options. The first one is swapping two rows. Here an example of that and the R notation of that. R notation is simply R, which stands for a row, and the subscript stands for which rows are being manipulated and or changed. Another thing you will see later is R star and then subscript. That means that is the row that is being changed. The next row reduction allowed is applying a non-zero scalar. Here an example of that and the R notation again. You simply multiply each element in the row by the same number. The last row reduction option is adding and subtracting two rows together. Here's a basic example of that along with the R notation. You can also put a scalar on one of the rows to get a certain row to where you want it. Here's the R notation for that as well. Now, the goal of Gauss-Jordan elimination is to use these row reductions to get the system of linear equations into reduced row echelon form. You must have leading ones and zeros everywhere else in that column of leading ones, as shown in this example. Now let's do an example. Here is a set of linear equations. Always start by putting it into a matrix. Now let's follow the steps to get it into reduced row echelon form, also called RREF. So first we'll get the uppermost value to 1, which is already done. Next we'll get all the entries below the 1 into zeros. So R2 is equal to R2 minus 4R1. Step 3 is to get the diagonal to below and to the right of that first one to be 1 as well, which would be this value of -3. To do that, we must use a scalar row reduction. Step 4 is to get the rest of the column to 0. Now we have finished. As you can see, it is in reduced row echelon form. And now you simply read the coefficients back into their variables and read off the answer. Now that you know how to use Gauss-Jordan elimination, you can solve any set of linear system of equations. Have a great rest of your day and see you next time.